Hi, I'm Zimin Xia from Intelligent Vehicles Group at TU Delft. I will present our paper, SliceMatch Geometry-Guided Aggregation for Course Pulse Estimation. For intelligent vehicles, a rough estimate of each vehicle's location is often available, for example, from GNSS. In this case, given a ground-level image taken by the vehicle-mounted camera and an aerial image that covers the ground camera surrounding, we aim to accurately estimate the 3 degrees of freedom ground camera pose inside the aerial image. For this task, we propose a method called SliceMatch. It sets a new state of art on VIGOR and KD datasets. The design of SliceMatch explicitly considers a geometric relation between ground and aerial views, and it uses coarse view attention and contrastive learning. With our design, SliceMatch is highly efficient. It runs significantly faster than previous state-of-art. Our code can be found through the link. Now we explain SliceMatch in more details. Assuming the ground camera has small pitch and roll angles, we exploit the geometric relation between ground and aerial views such that at the ground truth pose, the triangle-shaped sizes in the aerial view correspond to the vertical sizes in the ground view. For the task of camera pose estimation, SizeMatch constructs a size descriptor for each ground and aerial size. The final ground and area descriptors are constructed by concatenating size descriptors. During training, we maximize the similarity between ground descriptor and the area descriptor at the ground truth pose, while minimize the similarity between ground descriptor and the area descriptors at wrong locations or have wrong orientations. To efficiently achieve that, we have the following considerations. First of all, for pair of input, the feature extraction should be done only once, independent from the number of poses we want to test. After feature extraction, we propose a novel feature aggregation module that guides us feature within sizes at different poses. This is done efficiently by having pre-computed size masks at each candidate pose. Once we acquired the descriptors, testing candidate poses is done by matrix multiplication, which is highly parallelizable. The input to SliceMatch is a pair of ground and area images together with a set of candidate camera poses. Convolutional feature extractors are used to extract ground and area features. In the ground branch, an attention module is used to reweight the feature at each spatial location. Then we divide the ground feature volume into n vertical sizes, and for each size, generate a size descriptor. Each ground size descriptor describes the scene in each of the n viewing directions within the ground camera's field of view. The final ground descriptor is a concatenation of n ground size descriptors. In the area branch, we propose a coarse view attention module that reweights the area feature based on the similarity between the extracted area feature and each of the ground size descriptors. Recall that each ground size descriptor describes the scene in a specific ground viewing direction. Therefore, we require n-reweighted area feature volumes that correspond to n viewing directions in the ground camera's field of view. Given each of the candidate poses, we pre-compute n area size masks, simulating n viewing directions if the ground camera locates at the candidate pose. When the ground image is panoramic, we use the viewing direction of the center vertical line as the camera orientation. As shown here, when the camera points to the southwest, the n size masks here correspond to a panoramic image taken at this pose. We aggregate area feature inside each size into descriptors by multiplying the feature volume with the size masks and then summing the features. Similarly, the area descriptor is a concatenation of n area size descriptors. Finally, we require a set of area descriptors for the input set of candidate poses. In inference, we take the argmax of the cosine similarity score map as our pose prediction. Since the feature extraction is done only once, and the size masks at fixed candidate poses can be pre-computed, SizeMatch can run very efficiently. For example, it runs at over 150 frames per second on a standard workstation with a single V100 GPU, which is significantly faster than previous state-of-art baselines. And shown in the plot, we didn't observe runtime overhead when testing more candidate poses. In our quantitative comparison to state-of-art baselines, with the same backbone feature extractor, SizeMatch beats all baselines in all tested use cases. With a more advanced backbone, the error in pose estimation further reduces. Please find our comparison with more baselines on more datasets in our paper. SizeMatch's pose estimation is achieved by comparing ground descriptor to area descriptors at different poses. Thus, when there exist multiple visually similar locations, it can express its multimodal uncertainty. The red color denotes the descriptor matching scores, and the darker color, the higher the matching score. Green means ground truth, and blue is a baseline method. Yellow is our final prediction, which is a base scoring candidate pose. In the second example, the ground image has a limited field of view, and on this challenging example, our prediction is still accurate. Please find more details and results in our paper. Thank you and see you at our post session.